The return trip with the wind takes only 1 hour. So we're asked to find the total flying time for the round trip if there was no wind at all. So I'm going to label my chart. I'm going against and then with the wind. And against the wind, I'm going slower. And with the wind, I go faster. My travel time against the wind is 1.5 hours, and my travel time with the wind is 1 hour. And round trip 600 is the distance for both. So I'm going to keep this really simple and just set up a straightforward equation using the first row. And then I'll switch colors for the second row. And then just come back and clean up so I can set up my little systems. So dividing 600 by 1.5, I end up with r minus c equaling 400. And then the other equation, very straightforward. And so this becomes my system. So I have a simple little system here to solve. And I'll just go ahead and put the blue equation underneath the red one and we'll solve it. So this is my system. So the 500 represents my flight time without the wind at all. So if r equals 500, if that's all I was asked to find, I would be done. But it says find the total flying time for the round trip if there was no wind. So I'm looking for time. That would be distance over rate. My distance was 600. With no wind, my rate would have been 500. And this reduces down to, or simplifies down to 1 hour and 12 minutes to answer the question completely. So 1 hour, 12-minute flying time with no wind. Okay, number 16. 1,080 kilometer trip from Madrid to Paris takes 2 hours flying against the wind and 1.5 hours flying with the wind. Find the speed in still air, so that's finding my R, and then find the speed of the wind, and that's the current. So this is fairly simple. I'm going against and then with. And against is R minus C, and with is R plus C. 2 hours and 1.5 hours, and it's 1080 both ways. And the process is the same as the previous. We'll just keep this really simple and straightforward. And then I can switch and then cleaning these up a little bit to create my system. So here's my system of equations, and I'll just write the blue underneath the green, and we'll solve it from there. So this is my system for solving. So my rate in still air, 630 kilometers per hour. And then the rate of the current, well, I could take either equation, just go back to the green equation, and if I let R become 630, I can see that the rate of the current is 90. So the rate of the wind is 90 kilometers per hour. Number 18 is slightly different, but it's still the same logic. A motorboat has a 4-hour supply of gas. How far from the marina can it travel if the rate going out against the current is 20 miles per hour and the rate coming back with the current is 30 miles per hour? So once again, labeling the chart, against in width, and my rate against, actually I'm straight out given that, so my rate against the current is 20, and then my rate with the current is 30. Time is the different column here. I have a 4-hour supply of gas. So if I use T hours going one way, then I have 4 minus T. That's the amount of time that I have left. So then my distance column would look like this. And since this is a round trip, this is where I would use the relationship of distance equaling distance, or RT equaling itself. So to set this up for solving, and running through the algebra, which everybody's capable of doing that, I end up here. T equaling 2.4 hours. And then the question says, how far from the marina can the boat travel on this 4-hour supply of gas? So I would go back to my distance column, this is as good as any, and I would substitute in 2.4. And that lets me know that the boat can travel 48 miles on this supply of gasoline. And it checks, if you do the same thing in the 30, it checks there as well, 48 miles. And the last problem we'll look at is number 20. The rate of the current in the Susanna River is 4 kilometers per hour. If a canoeist can paddle 5 kilometers downstream in the same amount of time she can paddle 1 kilometer upstream, how fast can she paddle in still water? So once again, we're going up and down. And upstream, we're slowed down. And here, we're told that the current is 4. So we're told that C is 4. So when I go into my rate column, upstream is R minus 4, downstream is R plus 4. And I know that she travels 1 kilometer upstream. Let's see, she can paddle 5 kilometers downstream in the same amount of time she can travel upstream. And time is the equal factor in this problem. So to set up the equations, time, remember time can be thought of as D over R. So time here would be 1 over R minus 4, and time downstream would be 5 over R plus 4. So I set up my ratios. And I have a nice cross product problem. It's easy enough to solve. And I will give you the answer and leave it to you to do the algebra behind this. You're all capable of doing that. How fast can she paddle in still water? After cross products, R is 6, so it's 6 kilometers per hour.